All right, everyone, like we talked about yesterday, there's essentially a 5-step process that you go through when you solve a more difficult force problem, or really any force problem, but more difficult ones especially. And so that 5-step process, as we discussed yesterday, the free body diagram, make sure you know what coordinate system you're using. Usually it's the standard one, sometimes it's not. We'll see that soon actually. If you need to do vector decomposition, if any vectors don't align with your x or y axis, you got to do vector decomposition. Then we apply Newton's laws in one or more dimensions. We'll see 2 dimensions today. And then apply either Newton's first law or Newton's second law. Newton's first law applies when the acceleration is 0, and that implies that the net force is 0. Newton's second law applies when the object is actually accelerating. The acceleration is not 0. And then the net force is equal to the product of the object's mass times its acceleration. And when we do that, we set up some equations, and then we use those equations to solve for our unknown. So we're going to do this problem now. It's the one where we have 2 masses set up like this. You might have seen a system like this set up in front of a class this year. I'm going to call this guy M1 and call this guy M2. And it's kind of weird because we're not given values for these masses. We're given their values as integer ratios, or integer multiples, I should say, of some unknown value m. So in my particular, everyone will have different numbers here, but in my particular one, m1 is 30 times m. So we don't know what m is, but whatever it is, m1 is 30 times it, and m2 is 8 times m. So m1 is obviously more massive than m2 in this case. We are neglecting friction though. If we are neglecting friction, then no matter how small this guy is, he's going to cause acceleration because there's going to be no force, as we'll see, opposing the motion. All right. So I'm just going to go through my process here. Free body diagram. Since I have 2 objects, I have to draw 2 free body diagrams. So I'll draw the one for M1 first. On M1, obviously it has a weight force. That's the first force I always draw, is the weight force. And we know it is the force of gravity, but we also know the force of gravity is equal to an object's mass times the acceleration due to gravity, for reasons we'll learn about very soon. And we know that there's a normal force. We have a normal force there because the object is at rest on a surface, and when objects are in contact with surfaces, those surfaces exert forces. And those are called normal forces. Excuse me. And we know actually Newton's first law applies in this direction, in the vertical direction for M1, because the object isn't accelerating in the vertical direction. So these guys have to be exactly equal to each other. And then we also have tension in the string pulling to the right. So I'll call that my tension force. Okay? If there was friction acting on M1, it would exert a force to the left, but there's no friction here, we're neglecting it, and so that's the free body diagram for M1. Go ahead and draw the free body diagram for M2. M2 is the hanging mass. And so I know that there is, I know that there is a downward weight force on M2. So let me draw that guy. So that's actually M2G. I should have written M1G here because there's 2 different masses. And then we also have the tension force acting on this object pointing up on M2, pointing up. And we are also assuming an ideal pulley. And as we discussed, if we're dealing with ideal pulleys, massless, frictionless pulleys, these 2 tensions, the tensions on either side of the pulley will be the same. All right, so there's our free body diagram. So no other forces acting on M2. All right, now I can apply Newton's laws. What are we trying to find here? We're trying to find the acceleration of the descending block. So let me actually write that up here. We are asked to find the acceleration of M2, which will be going down. All right, step 1's done. Step 2, let's talk about our coordinate systems. This is where it gets a little weird. M2 is accelerating downward. It makes it easier mathematically, less negatives to worry about, if when an object is accelerating, you call that the positive direction. So I'm going to say that the positive direction for M2 is down. I know it's kind of weird, but I'm telling you, it makes the math easier. The thing is, oh, and also M2 doesn't have any forces in the horizontal direction, so we don't need to worry about it. The thing is that the motion, and you can hopefully convince yourself of this, whatever motion M2 has vertically, M1 has the matching motion to the right and to the left. Okay, so just think about that. But whatever M2's acceleration down is, that's going to be M1's acceleration to the right. So bear that in mind as we go. So for M1, I'm going to use I'm going to use the standard coordinate system for M1 because then I don't have to do any vector decomposition. But I just want to note that in the x direction, that motion is identical to M2's vertical motion. All right. Since we are asked to find the acceleration, I'm going to apply Newton's second law. And I have two objects, so I'm going to apply Newton's second law to both objects. So for M1, I will say that the net force on mass 1, which I'll put the subscript 1, is equal to mass 1 times his resulting acceleration. And then I got to unpack. I got to unpack what sigma f represents for M1. Specifically, I should say M1 in the x direction, because I could be doing this in both directions, so oops, still early. So the net force on M1 in the x direction will be that mass's mass times its acceleration. And that net force in the x direction, there's only one. So all we need to write, when I unpack this, all it ends up being is that tension force. That equals mass 1 times the acceleration. Note that I'm setting up an equation for mass 1 even though the problem's asking about mass 2. Well, I know if I can find the acceleration of mass 1, it's the same as mass 2. They're just like this. As mass 1 goes to the right, M2 goes to the down. All right, but I can't actually solve for the acceleration because I only know information about M1. If you look at the answer choices for this particular problem, there's no answer choices with tension in them. So if I divide both sides by M1, I'm not going to see that in the answer choices. Therefore, I need to do a little more work. That tells me, the math tells me I need to do a little more work. Well, where does the other work come in? Analyzing M2. We can always, if we got two objects, we can always write at least two equations for their motion, for the forces acting on it. So for M2, the math works out. The net force on M2, and I don't really need to specify direction because we know what direction it's moving. It's only moving in one direction. It's going to be mass 2 times that resulting acceleration. And remember, these two accelerations are the same. They're the same magnitude, right? Now the net force on mass 2, there's two forces here. And down is my positive direction, so in that coordinate system, my positive force when I unpack sigma F2 will be M2G minus the tension force equals the mass 2 times the acceleration, okay? All right, now I'm getting somewhere because I see an acceleration here and an acceleration here. Really my only two unknowns. Really, I don't know the masses, but I have expressions that will allow me to get to get an answer that will match one of the answer choices. So in this case, I have a system of two equations. So I see the easiest way for me to do this one. I see that the tension force equals M1A, so I can just plug in the tension force. I can plug in M1A for the tension force here. When I do that, I just rewrite M2G minus M1A equals M2 times A. All right, well now I see two terms with acceleration in them, so I got to combine them. So I'm going to add M1A to both sides. And when I do that, I just bring down M2G. And that's going to equal, now I just add these together, M2A plus M1A. And now I can, the six-letter F word, I can factor an A out of both of these terms, and then I'll be able to solve for it. So when I factor an A out of both of those terms, I get the acceleration is equal to just the sum of the two masses. All right, and then to solve for the acceleration, I just divide both sides by M2 plus M1. Cancels on this side. The acceleration is now by itself. I'm going to go ahead and bring this up to the top. The acceleration now is M2G divided by m2 plus m1. But as you'll probably notice when you look at the answer choices for this problem, that is definitely not one of the choices. But then I forgot this right here, right? I have expressions essentially for m1 and m2. So I can plug those into that equation. So I'm going to rewrite that equation here. The acceleration, our result when we did our force analysis was m2g divided by m2 plus m1. Well, now I just replace m1 with 30m, m2 with 8m, and let's see what happens. So I replace m2 with 8 times m, so I get 8m times g, divided by m2, which is 8m, plus m1, which is 30m. Well, the denominator here, those are like terms. That's like 8x plus 30x. We can combine those. So I have 8mg over 38m. And I can definitely simplify this. First of all, I have a numerator m and a denominator m, so those cancel. And then I can reduce 8 over 38 to 4 over 19. Don't quote me on that. So that'll be 4, writing it as the answer choices have it, this would be 4 over 19 times g. That's my answer. And notice it has that weird, it's written, the acceleration is weird with the, written with the weird absolute value symbols, but with 2 of them. That's essentially the same thing as absolute value, but for physics, it just means magnitude, right? Just the magnitude of the acceleration. So for me, the answer was this. Your answer will be different, but this is how you go through that solution. Hope you enjoyed.